Cool, yeah. So all of AQA are A-level chemistry, organic, topic 10 pattern, yeah. All of aromatic chemistry, yeah. Alright, so you know, let's get started then. Let's jump into the mix, as they say, yeah. Alright, calm. So what is benzene, yeah? So obviously benzene is a cyclic, so that means it's like a circular kind of component, yeah. Planar compound that consists of the formula C6H6, yeah. Each carbon, yeah, is bonded to two other carbons as well as one hydrogen atom, yeah. Hence, since carbon has four valence electrons, so four electrons in the outer shell, there is a lone pair, yeah. Since obviously we used up two electrons with my man with the other carbons, yeah, and we used up one electron with hydrogen, yeah. You get it? So C, and then one lone electron pair, yeah, which is in the p orbital, and obviously the p orbital has a shape, yeah. So therefore, since it's in the p orbital, yeah, we're gonna have that kind of shape above and below the plane, yeah, and obviously this is planar, yeah. Alright, calm. The lone electrons here, they form a delocalized electron ring, yeah. So hence all the CC bonds have the same bond length, yeah. So basically, this p orbitals here of delocalized electrons, they create like a little ring, yeah. So a ring above and below the plane, yeah. That's gonna be a delocalized electron ring, yeah. So they're not localized in small points around the carbons, they're delocalized, electron density, yeah. Alright, calm. And the CC bond length here is between that of a single bond and a double bond. So a CC single bond is 0.154 nanometers, yeah. A CC double bond is 0.134 nanometers, and the one in benzene is 0.140. So effectively, yeah, it's like as if you got alternating CC bonds and C double bonds, yeah. It's like that. It's like alternating ones but combined together in a certain way. You get what I'm trying to say? Alright, cool. So you got Kekule, yeah, structure, and delocalized structures, yeah. So Kekule structure, basically, this is before they thought about the delocalization, yeah. So what they initially thought was, due to this, changing in electron lengths, yeah. What they thought is it must be an average, right? So there must be like a double bond, and a double bond, and then three single bonds here that are alternating. And then if you add the bond lengths and divide it by six, yeah, you're gonna get the average one for each one, which is what they would have thought initially, yeah. Obviously, this is not true, it's delocalized, which is why we draw it as a circle now, yeah? But this one over here is still common, yeah? You'll still find it a lot, and you'll still find it in A level as well. So there you go, yeah? Come proving benzene's delocalized nature. So benzene is more stable than the theoretical cyclohexatriene. So cyclohexatriene is this situation here, Kekule's one, yeah? That's cyclohexatriene. It's a theoretical version of this without the delocalized ring, yeah? So when we hydrogenate, yeah, cyclohexene, it has a enthalpy change of minus 120 kilojoules per mole, yeah? So the enthalpy change of hydrogenation, yeah, of cyclohexene, hexene, yeah, is minus 120, okay? No problem. Cyclohexene only has one double bond there, so as you see, we hydrogenate, yeah, we only get, has one double bond, we get minus 120. So for this theoretical cyclohexatriene, it's got triene, it's got three enes, it's got three double bonds. So therefore, I'm going to need to times minus 120 by 3 to get what it's going to give me. So times it by 3, yeah, you're going to get minus 360. So hence, this benzene, yeah, benzene, when I do hydrogenation, yeah, it should give me minus 360 because that's what we predicted. Because benzene, we think any theoretically, has three double bonds. So if it has three double bonds, therefore it must give us minus 360 because when we had one double bond, it gave us minus 120. Yeah, however, when we actually do the hydrogenation of my man, it's way lower. The hydrogenation of benzene is actually minus 208 instead of the predicted minus 60. So that means that benzene doesn't have three double bonds. Instead, it's more stable than cyclohexatriene because remember, when you're releasing energy, you're making bonds. So therefore, less bonds have been made so because it's harder to break those bonds. Do you see what I'm saying? So more energy, if it's less negative, yeah, it means more energy had to be put in to break the bonds. So therefore, yeah, since more energy had to be put in to break the bonds here, it means it's more stable and the bonds require more energy to break, yeah? So therefore, this proves the delocalized electron structure. This proves that the localized structure that's going to be more stable, and that's why it does not have double bonds and single bonds alternating. It has this kind of situation, and that's what they want to see you say in the exam as well. Alright, safe. So why is the localized electron structure more stable? Yeah. So why does that make it more stable? Well, obviously, if benzene had an isolated single and double bonds, yeah, there would be like localized electron densities, yeah, which would lead to obviously more instability. Is localized. It's not all in one system. Hence, it's obviously it makes it more reactive as well because electrons are going to be wanting to leave, more reacting stuff like that, and it just makes it less stable in general. It's like if you're holding hands and one guy's holding you with two hands and then one guy's holding with one hand, and then one guy's holding with two hands. It's less stable compared to if everybody just holding with one hand, and it's all firm grip, one hand overall. It's like it's a balanced charge. It's like more dissipated overall on the whole thing. Calm, naming arenes, yeah. So obviously an arene, yeah, is any molecule that contains that benzene ring, yeah. So that benzene ring is that carbon ring, and so any molecule that has that is called an arene, yeah. So this could be a methylbenzene, that's an arene, dimethylbenzene, yeah. All of these chlorobenzene, nitrobenzene, bromobenzene, whatever, yeah. And obviously, when you have these kind of situations, the name of the functional group goes in front, so whatever the attachment is, so like methyl, chloro, nitro, and then benzene at the end. So it's pretty easy to name, yeah. However, the only other example, yeah, is when you have phenyl, yeah. Phenyl is the benzene ring with the OH attached to a hydroxy group attached to that, yeah. And also an NH2, they also count it as that. So that would be phenyl, yeah. And yeah, and this would be like phenylamine on the right here, yeah. So that's the situation there. That's the only exception. Calm. Electrophilic substitution, yeah. So as you lot know, or you don't know. Yeah, we got electrophilic addition up to this point in the course here. Now you got electrophilic substitution, yeah. So because of the delocalized ring of electrons, yeah, benzene has a high electron density, yeah. Same way how when we had electrophilic addition, that's when you have an alkene. There's a high electron density in the double bond, yeah. So here we got high electron density in that ring of delocalized electrons, yeah. So hence electrophiles are attracted to this because electrophile, yeah, it means it's philic to the electrodes. You know what I'm saying? So it loves electricity, it loves electro, it loves negative charge, it loves electron density, yeah. So therefore, because benzene is so stable, it can't undergo electrophilic addition because that would add shit to it, and then it's gonna get destructed in it. It's gonna, it's gonna break the stability down. Yeah. Why would benzene, already very stable structure, react with some shit to add some shit? It's not gonna happen, is it, bro? So therefore, yeah, it's gonna need to undergo substitution. One of the H's is gonna need to be substituted for something else. Yeah. So therefore, we got electrophilic substitution, not electrophilic addition. And this is like the easiest mechanism in A-level chemistry. Yeah. It's very easy. Look. Yeah. Alright, safe. So let's look at the reaction mechanism here for electrophilic substitution here. So we got the benzene ring here. We got the electrophile here. Remember, electrophile is positive here because attracted is a negative here. Alright, calm. So you got the so let's say here you got the electron density ring right there, yeah. Obviously that ring is going to be attracted to the A plus, yeah. So the electrons are going to be attracted to the electrophile, yeah. Since that's positive, the electrons obviously negative, it's just going to be attracted there, yeah. That's going to break the stability of this because it's acting like it's like breaking a bond, but because it's not a bond, it's a ring. It's like breaking part of the ring. You get me? So it's going to create like a an intermediate kind of thing, you know. So obviously draw that, and now this is the important part, yeah. You see where the thing is acting, so it's going to be on the top here, yeah? That's where A is going to attach here. Now, listen, obviously right now there's obviously a H attached to that already, yeah? So A is going to be joining onto that since it bonded with the thing, yeah? Now, when you draw this destroyed ring, yeah, you need to make sure that it starts and ends between the adjacent carbons of where you're attaching it to, yeah? If you don't do that, you might lose a mark, yeah? So you need to make sure that's done. And it becomes positive charge since it lost electron, yeah? And obviously because of this, A has now joined on, yeah? And obviously this can't happen. This is an intermediate. Obviously it can't be bonded to like that at the same time. So obviously what's going to need to happen here is this electron goes there to reform the ring. And so therefore H is going to, fuck off. And you're just going to get, and this happens quickly as well. This is the rapid step here. And you're going to reform the ring here. And then you're just going to have A instead of H. Yeah, and then plus H plus here. So that's the mechanism. Yeah, it's very easy. You can substitute A for any electrophile here. You'll see in a minute. I'll show you with nitrobenzene. So very easy mechanism, bro. That's it for electrophilic substitution. Not really much here to do, yeah. Alright, so Friedel cross acylation, yeah. So for Friedel cross acylation, yeah, it's basically used to make an acyl group, yeah, onto a benzene, yeah. So what you're gonna do is you're gonna add an acyl group onto a benzene, yeah, to make it weaker and easier to react to form, useful compounds that you can use in your day-to-day life and you can use around you and stuff like that, yeah. So obviously, why we're doing this is because obviously benzene is very strong here. So therefore, if you want to make shit from it, you got to weaken it first so it can react, so you can make shit from it, yeah. Obviously, the benzene ring is so strong, yeah, a very positive electrophile is needed, yeah. So the ROC group alone, the acyl group alone, is not enough to act as an electrophile, yeah. It needs to be made even more positive, yeah, to be an electrophile for this situation. And hence, we need to react it with a halogen carrier such as AlCl3 to produce an even stronger electrophile, yeah. So that's the preparation step, yeah, at the start, yeah. So Friedel-Crafts acylation equation, yeah. So the Al3 is gonna accept electrons from the acyl group, yeah. So this acyl group is the RCOCl. It's gonna accept electrons from the acyl group, yeah, and hence a carbocation is formed that is extremely positive. So it will accept the Cl minus from the Cl group, and that RCO is going to turn into RCO plus here. So this RCO plus is going to be a positive electrophile now, very positive electrophile. That's then going to be reacted to form to undergo Friedel-Crafts acylation, yeah. And listen, also on top of that, yeah, this equation here, yeah, is very important to memorize. You need to memorize this equation here because they love asking this. They love asking state the equation for Friedel-Crafts acylation, yeah. So make sure you memorize this equation because they'll ask you in the test and it's easy marks. Alright, come on. Reaction mechanism, yeah. So the product of the reaction is going to be a phenylketone, which is again is a lot unstable and shit like that. That means you can use it to make dyes, pharmaceutical, and explosives. You can use it to actually make things, yeah. And as you see in the mechanism, AlCl3 will be reformed, and hence it was acting as a catalyst here. So now you're going to see the reaction in a minute here, yeah. So here's the actual reaction mechanism here. So again, this is going to be electrophilic substitution, obviously, yeah, because we're dealing with arenes here, yeah. It's always going to be that with arenes. So let's draw the benzene ring. Draw it on the side, it's not that much of a problem. Calm. So we got the benzene, and then we're gonna have the electrophile that we produced in step one, or in other words, the acyl group here. That's gonna have a plus onto there. So now, obviously, what's gonna happen is you got a positive there, you got electron density here, so electron density is attracted to the plus. So simple electrophilic addition, substitution is gonna be attracted to that there, yeah. Alright, calm. Because of that, obviously, it's gonna join on, yeah. It's gonna join on here, bro. We're gonna get C, I don't know what I said. Gonna get CrO. And then also attached to this is obviously the hydrogen that was initially there, yeah? Because remember, there was a hydrogen there initially, yeah? It's a skeletal formula, yeah? And now this one, again, so make sure you draw the circle between the adjacent carbons, yeah? Alright, safe. And then plus there, obviously the inside was destructed, you got plus there, yeah? Alright, safe. So now what's gonna happen here is this is gonna turn into what? This is gonna turn into the same thing. Oh, now this AOCl4 that was created as well in the preparation step here. It's gonna look like that. Obviously negative here because Cl minus attached to it here. This is obviously unstable. It's gonna want to react here. It's gonna want to get rid of this negative charge because you've got four Cls around it. So what's gonna happen here is obviously this is gonna react. One Cl is gonna react with the H here, obviously here. So that's gonna react with the H to make HCl. And then obviously, therefore, this bond is useless now. This bond's going to react. It's going to go back to reform the carbon delocalized ring here. So that's what's going to happen there. And then you're going to just make the final product here, which is going to be. It's where it is, bro. Which is going to be that plus HCl, and then plus obviously the AlCl3, yeah, from over there. Yeah, because that lost one Cl, yeah, and obviously that means that this is a catalyst here. So that's the reaction mechanism, yeah, for Friedel-Crafts. So this is the second part here. Second reaction mechanism you need to know. That's a specific example of electrophilic substitution here. Is going to be production of nitrobenzene here. So when concentrated nitric acid is heated with sulfuric acid, nitrobenzene is formed here. However, obviously a strong electrophile must be produced first, then to react with the benzene. And that's obviously the nitro here. The NO2 plus here, that's going to be the strong electrophile that's going to react with benzene to make a nitrobenzene. So you need to spawn that in the first place here. And to spawn that in, basically, what you need to do is you need to mix hydrochloric acid here with HNO3. That's going to produce H2NO3 plus here, plus H2SO4 minus here, HSO4 minus here. And again, make sure here you memorize the equations here, because it's important. They'll ask you for it in the future here. Alright, calm. Now this H2NO4 NO3 plus here is just gonna like dissociate or degrade or whatever the fuck you wanna call it, decay into H2O and NO2 plus here, and that's gonna form that NO2 plus electrophile here. Calm. And the nitronium ion is now reacted with benzene to form the nitrobenzene, yeah? And so I'm gonna show you the reaction mechanism now. Obviously as well, I don't know if I mentioned it or not, but you'll see that H2SO4 is also going to be reformed here from this situation, so it's acting as a catalyst here. Alright, come on. So the reaction for nitrobenzene production here. So again, the mechanism here, you're going to draw the nitrobenzene. Made the benzene here, and then nitro plus here, NO2 plus here. And now obviously this is going to react with that, so obviously you're going to be attracted to electrophile there. So you're going to do that. And then obviously you're going to again draw between the adjacent carbons here. So like that, it's going to disrupt the ring. Now you're going to get NO2 attached and then H attached. So it's just simple electrophilic substitution here, like earlier here. And then obviously this bond is going to break and it's going to reform the ring here. So therefore it's going to reform the ring there. The electron's going to join. It's going to create the delocalized ring again. And nice and easy. That means H got substituted for NO2. Now you just got NO2 here. And then plus H plus here. And that H plus will then reform from earlier to make the Alright, calm. And then the H plus is released here is going to react with HSO4, which was from earlier in step 1 here, to produce H2SO4 here. So therefore H2SO4 was a catalyst effectively here. And so the reaction must be done at 55 degrees Celsius here to ensure a mono substitution here. Anything that's bigger than this is going to lead to multiple substitutions here. Alright, calm. Uses, yeah. So obviously, dyes are produced when nitrobenzene is reduced into aromatic amines, yeah. That's why it's important that only one substitution occurs, yeah, because that one substitution, like this can only occur, can only reduce into aromatic amines if it was one substitution, yeah, that was done. And or TNT or trineutral yeah, is also produced from nitrobenzene, yeah. Toluene apparently is just methylbenzene in it, so it's just another word for that. Alright, calm. And that's it, man. No need to waste time here. No need to put no TNT picture or some bullshit here like the other man probably doing. Yeah. Just straight gun. That's it, bro. We're out here, fam.